Welcome to 329. This is a Programmable Logic and Microprocessor design course, and today we'll talk about Programmable Logic. First, a little bit of history. We can see that the number of gates that we have per chip has really increased. And so CPLDs are kind of an older technology than FPGAs, but both were started around the middle of the 80s. Before that, we had other programmable logic devices, but they were one-time programmables, typically. Okay, so CPLDs and FPGAs have advantage over discrete logic, like individual gates, like flexibility, board space, time to market, because we can actually use a hardware description language to program them, and we know this from CPE 229 or 233. So designs are implemented on programmable logic devices like CPLDs or FPGAs through Programmable Elements. And programmable elements include wiring nets as well as memory cells. So just kind of programmable elements can fall into the one-time programmable thing category. That can be, and they're nice because they're non-volatile. They can use fuse or anti-fuse technology. So basically, to create an open or a short, you blow a fuse by sending a higher current than through the system in a specific manner. And then we have reprogrammable ones, volatile ones that just use RAM. And then non-volatile ones that use flash. So the Spartan 3Es that we use in CPE 233 or 229 use volatile and RAM. There's flash on the board, and you can program the flash on the board. But some FPGAs or CPLDs have embedded flash memory or EEPROMs, which is a different type of flash memory, basically. So if you do a little taxonomy here, one-time programmables are here, and they're non-volatile. EEPROM, EEPROM, and flash can be done here, and then SRAMs are here. I guess one word about the EEPROMs is so flash or EEPROMs are the oldest technology. What they actually do is there's a floating gate on the transistor, and what we do is we use tunneling to put some charge on the floating gate, and to erase the that charge on the floating gate, then creates makes the source and the drain connected, right? Just like a regular transistor. Now, to erase it in an EEPROM, you actually had to bathe the chip in UV light for, I don't know, maybe 30 minutes or so. So we'd actually put like a quartz window on top of the chip, and then we'd bombard it with UV light, which would eventually knock off all those electrons on those floating gates. So EEPROMs came around, and we can actually, the way we erase these is we actually modify the body voltage, the back body voltage, and basically create tunneling to go the other way, which tunnels off all of the electrons on this floating gate. And then flash is similar to EEPROM, except they're organized. These floating transistors with floating gates are organized into strings. So in EEPROM, you can typically read or erase smaller sections of memory, whereas flash, it's usually a larger section of memory you have to erase at one time. Actually, for flash, you actually have to read it first, modify, then write it back to actually write new data. Okay, so we'll talk about, I guess we're at Xilinx house here, and we'll talk about CPLDs versus FPGAs. In general, CPLDs can use oftentimes use non-volatile programming elements, but some do use volatile. And then we have the Spartan FPGAs use volatile programming elements, and usually FPGAs have more logic on them. Okay, so CPLD architecture kind of looks like this. It's essentially we have some number of inputs and their complements generated, and each of these X's here means a connection. So this is kind of shorthand here. This is a giant AND gate with some number of inputs here that we can actually attach. So these X's here are actually a memory bit, and says so if there's a 1 here, this connection is actually made to this AND gate. So this AND gate could have some number of inputs here, X0 through Xn. And so we have a set of AND gates and then an OR gate right here. And so this is like sum of products right out of 129 or 133. And so that's how we generate logic out of this. And then here we have an XOR gate, so we can actually invert everything as well if we wanted to. Again, each of these green blocks here is also a memory bit, an SRAM bit, or some sort of memory bit. Then we have a flip-flop here that we can use optionally, right? Because we can either use the output of the XOR here or the output of the flip-flop here, and it goes out through a buffer. We have some sideways inputs too, so these can come from, this is a global output enable. This is some extra data that we could also route in through here from the next macro cell that's next to it. So general CPLD is made out of an and/or plane or a macro cell. Okay, that's the jargon. And so we'll have a whole bunch of macro cells in a CPLD, and the inputs here, there'll be some number set of inputs and some number of outputs, and we also have some buses that allow us to actually move data from higher macro cells down to lower macro cells and things like that. And then so a whole bunch of macro cells put together is called a macro block, and we'll have several of those on the chip, and then there'll be a sea of programmable interconnect, which we'll talk about a little bit more in a few slides. Okay. Beyond that, if you look at the die of the chip, there's probably some I/O blocks here as well that allow you to take inputs and outputs on the chip. FPGAs are structured quite a bit differently. We do have muxes, and the muxes here, right, there's two memory bits here that allow us to connect any one of these four inputs to the output of the mux. We also then have a lookup table, which is just here this is showing a for LUT here, where we have 1, 2, 3, 4 different values here that we can spit out. And using a lookup table, we can actually create any form of data. And then we use pass transistors or maybe transmission gates here to route data through wiring, essentially. And so these lookup tables here can actually, if you think of a lookup table at the simplest, it could really just be the truth table of a gate, for instance. And the larger the lookup table, the more memory it has, the larger the truth table that you can implement right in the lookup table. And so that's how we're going to build. That's kind of our element, that programmable element that we're going to use. Then most FPGAs also have some sort of fast carry logic that allows us to support addition, because a lot of people like to do addition on FPGAs. A whole mess of flip-flops or state elements, and then a whole mess of muxes that allow us to flexibly route data. And so all of those things will be in these logic blocks here, using so there'll be LUTs in memory and FPGA, but there'll also be hard, maybe block RAM here, block RAM. And so actually your Spartan 3E has 8 KB banks of block RAM. I think it's either between 4 or 8 of them that you can use in your project. And then some clock management tools, and then I/O buffers again. Okay. Newer platforms actually include other things, let's say like an ARM processor here, so the new Xilinx Zinc architecture, FPGA architectures use ARM Cortex processors as well as logic blocks, and so they're pretty flexible, like systems on chip. Okay, so we'll talk a little bit about programmable interconnects, since both the CPLDs and FPGAs use them. There's going to be several levels of interconnect. There's going to be direct interconnect, like one neighbor to the next. Then there's going to be some local interconnect, provides kind of connectivity within a local region of configurable logic blocks or LUTs or lookup tables. And then there's going to be a global interconnect, so it allows us to provide connections across the chip. And then there's going to be clock and control wiring that'll allow us to maybe turn on output enables or route a clock across the entire chip. So how do we have this flexible routing architecture? Well, we use this diagram here showing N transistors, but it could be on transmission gates as well with a P transistor in parallel. And so here we have a set of wires here, and at this junction we have all these transistors. And if, say, for this transistor is on by putting a 1 in this memory bit, then this allows us to go around the corner this way. Likewise, if this was also 1, we could go around the corner this way. Or we could go through this way, or we could have a broadcast. So it's a pretty reconfigurable way of creating a network. And so you'd have a whole bunch of wires, a whole mess of wires on your chip, and each of these intersections will have 6 transistors at minimum. So basically I just said that this is kind of a silly animation, kind of shows some of the possibilities. So you could think, okay, in a CPLD, here's a configurable logic block, and here's another one. Here's 1, 2, 3, 4 of them, and we have these functions. We have function 1 that needs the A, B inputs, and function 3 needs the C, D inputs, and function 4 needs the results of function 1, function 2. So we need to route these outputs over here, and so you could imagine that when you're synthesizing, there's one section that says place and route. Well, the first thing place and route does is determine where to put the actual logic and CLBs, and then the routing is this process of trying to figure out how to make the connections. So when you're synthesizing, you'll see it place and route, and there's lots of little dots in the Xilinx ISE tool that you probably recognize. And so there's different types of interconnects, as I mentioned earlier. There's direct interconnect when you're just maybe talking to the next CLB, but there's also like a local interconnect here that allows several groups of CLBs to talk to each other, maybe several levels of local interconnect, and then there's a global interconnect. And so the fastest interconnects are going to be the shortest ones. So the place and router tools trying to minimize the delay for communication, and so placement of your logic in these CLBs can determine that, and also the routing. So here we can show that with a global interconnect, one here can go talk to, then using a local interconnect can actually go talk to 8, for instance. Okay, we'll talk a little bit about routing delays. And so we know from an inverter we have a pull down time, pull up time. And so we can estimate the delay of this in first order as an RC circuit. And the resistance here, the resistance and the capacitance is going to be determined by whatever we're driving. And so if we were pulling down here, if this was initially charged up and we were pulling down the output of this inverter, the pull down time is this R plus RL plus RC here. So RL is the load here, and this is the capacitance of the load. Or if we're pulling up, it's this way, right? And we can solve for the rise time. I encourage you to review this type of materials straight out of 307, right? It's not even 307, is it? It's like, I don't know, whenever you do first order circuits. And so if you plug in some constants here, for instance, it can be like 3 picoseconds could be the low to high transition. Okay, so if we apply this, we have a driver, and then we have maybe 2 interconnects here where the N transistors are on. You know, how does this affect the propagation delay? Well, the capacitance load here of the gates of this inverter is the same as the previous example where we had an inverter driving another inverter, but now we've added 2 pass transistors here, and so this adds essentially resistance in our model here. So we have RN here, and so the longer it goes, the more pass transistors we could go through here. Of course, the resistance becomes higher, and then the circuit becomes slower. So if we did that, we went from 3 picoseconds up to 5. So that's a definite slowdown in communication. Okay, so the rest of these slides are really just kind of FYI. You know, this is an example of how to build an 8-bit ripple carry adder. And so we'd have a full adder here, and the full adder, if you remember the sum, the sum is when it the sum is shown here, right, where the sum bit is basically if we have some number of odd inputs on, and the carry here is when we have at least 2 ones, so then we'll have a carry out. And so here's our 8-bit ripple carry adder. We'll have 8 full adders here, and the carry will ripple in between the blocks. So if we did it to a macrocell here, we'd need to, here is this will be the sum here, and this will be A1 is 1, B is 0, C is 0, or so P1, P2, P0, P1, P2 here are the cases where there's only one input is 1. Then we have to make sure that we also cover the one where all 3 inputs are 1, so we have some number of odd ones coming in. And so that would be our sum here, and then we can turn P4 off essentially by ANDing A with A naught, and of course that'll be 0. And then we just take an OR of that, and that's the sum. Likewise, the carry can be configured this way as well. And so that's a single full ladder. And so these full ladders, right, we'll have 8 of these maybe in parallel, and they'll have to talk to each other. If then an FPGA has a 5-variable LUT, then we can actually put 2 bits of addition all in the same lookup table. So basically, we have A0, A1, A2, B0, B1, and carry in. So 5 inputs, and we'll have 3 outputs. And so if we have a 5-variable LUT, we can put that'll hold 32 different possibilities for the outputs. And we'll just need 3 of those LUTs: one for the sum plus 1, and the carry out. And so then we can just chain them together using that flexible routing interconnect. Okay, so I think that's it for this slide set. Thank you, and goodbye.